Okay, well, we're back at it today, and we're going to move into section 3.3 and section 3.4 of the textbook. You'll notice I have posted some other videos to watch, some homework, a gizmo to use, and hopefully by doing all these things, we can get to understand all of these concepts. Remember, there's the questions discussion thread. If you have difficulty understanding anything, post a question in there and I will go in and answer it. So just a quick recap from yesterday before we move on into frictional forces. Yesterday we learned about something called weight, also known as the force of gravity, which is equal to the mass of the object multiplied by the gravitational field strength near the surface of the Earth, which is negative 9.8 newtons per kilogram. This equation right here only works for near the surface of the Earth, because this right here is the gravitational field strength near Earth's surface. You can actually calculate this gravitational field strength for any object. For example, if you use this equation right here and you put in the universal gravitational constant, the mass of the Earth, and the radius of the Earth here squared in the denominator, if you were to do that calculation, you would get 9.8 newtons per kilogram. If you decide to put in the universal gravitational constant, let's say the mass of Mars instead, and the radius of Mars here in the denominator squared, you would get the gravitational field strength for Mars, which is not negative 9.8 newtons per kilogram. Mars is a much smaller planet. You could do it for the moon. Put in the gravitational field strength. To find the gravitational field strength of the moon, you would put the universal gravitational constant right in here. Remember, we learned about that yesterday. 6.67 times 10 to the negative 11 newtons meter squared per kilogram squared. And you would put in the mass of the moon now and the radius of the moon squared in the denominator, and you would find a value that's not negative 9.8 newtons per kilogram, but a value that is about a sixth of that. The moon is very small. The gravity isn't as strong there. You could jump 6 times as high as you could there compared to here. If you're doing weightlifting, you could lift 6 times as much. So this will work for any moon, planet, what have you. The other thing we learned about yesterday was if you want to find the force of gravity between any two objects in the universe. All right, now when we say any two objects in the universe, we're usually talking about planets and stars, suns, moons, things like that. That's usually where it's used. Not exclusively, but usually. So if you want to find the force of gravity between the sun and Pluto, here's your equation. The universal gravitational constant, the mass of Pluto, the mass of the moon, and how far apart they are squared. All right, well, today we want to go to a new topic, as I said, from section 3.3 and 3.4. We want to talk about frictional forces. Frictional forces. Frictional forces, they always have one thing in common. They always oppose motion or oppose the start of motion. It's what's working against you when you want to move. All right. Now, what do these frictional forces depend on? Well, they depend on two things. The amount of contact between the object and the surface that the object is on. So how much force is the surface giving to the object on that surface? So the amount of contact is quantified by the force from the surface on the object. But we already know what the force from the surface onto that object is called, the normal force. So the more normal force that there is between an object and the surface, the more contact there will be, and the greater the force of friction will be. For example, if you try to drag a little baby, maybe sitting on a carpet, across a rug, all right, and then you try to drag a teenager sitting on a carpet, you try to drag them across the rug there, it's going to be a lot harder to move that teenager, not only because they're heavier, but because they have more contact with the surface and there's more friction there. So that's one of the things that decides how much friction there is. The other thing that decides how much friction there is what are the two surfaces involved? Do you have a wooden box being pushed along a wooden floor? Or do you have a wooden box being pushed along ice? Or do you have a plastic box being pushed along ice? All of these things here, we have to think about what are the surfaces involved that when I'm trying to push an object, when I'm trying to keep it moving or get it moving. So the object surface is one of the things that's involved in the amount of friction between two objects, and the uh, surface that the object is sitting on. So scientists have come up with a way to quantify this. And the way they've quantified it is through these two values. They are called coefficients of friction. And the symbols are mu s, that's for when you're starting an object to move. It's called the coefficient of static friction. And mu k, when an object is moving, but you're pushing it against the force of friction. And mu is, we've seen this letter before. It's the Greek letter. It's like a U with a little elephant trunk out in front of it. And scientists assign numbers to the two surfaces involved. Now these units, or these quantities, are unitless. They have no unit to them. They just tell you how much frictional contact is depending on the two surfaces involved. Now, there's no need to memorize these values. They're found on page 101 of your textbook. And I'll just give you an example of one. And what we have here, for example, is if you were to have an oak box being pushed along an oak floor, well, you would find on page 101 that scientists have assigned a value of 0.30 to it. So that's how much frictional contact is quantified because of the two surfaces involved. If you're trying to get the oak box to start to move on the oak floor, it's a different coefficient. It's the coefficient of static friction, and that's 0.40 right there. And if you see on page 101, it lists a whole uh, list of things. For example, steel on ice has a very low coefficient of kinetic friction. Look how low it is, 0.010. Rubber on ice, a little bit more. So as soon as you change the material involved, it changes how much the coefficient it is. So look at that, much smaller there as well. And if you take a look on page 101, you'll usually find that coefficients of static friction are larger than the coefficient of kinetic friction when you have the two same surfaces involved. So a good thing to remember is it's harder to start something moving than keep it moving. All right, once you've got it started to move, it's easier to keep it moving. It's always harder to start it moving. And one of the reasons is that the coefficient of static friction is larger than a coefficient of kinetic friction. So what I have here is a little simulation that I've also put a link to in here. And this is 50 kilogram object. And what we're going to do is we're going to push on it. And we're pushing on it with 50 newtons. So if I push on it with 50 newtons, the force of friction on it back is also 50 newtons, so there's no net force, so it's not moving. What about if I keep increasing it? Nope, still not moving, still not moving. I don't have enough force to overcome the force of static friction. So static friction is working against this person in the simulation pushing it. Look, we're all the way up to, what is there, 120. The object is still not moving. And then finally, we do get to when it's moving. Now, if you take a look at it now, all I need is 94 newtons to keep it moving. I'm not accelerating though. Look, the sum of the forces is still 0. I'm not accelerating, but I only need 94 newtons to keep it moving. That's a lot less than we needed to start it moving. Now, if I were to push harder, now I have a net force of 9 newtons. My applied force is 103 newtons. It's bigger than the 94 newtons that comes from friction. All right, so this object has a net force of 9. It's going to start to speed up. So let's reset that, and let's put this person on top of this. So now we've got 90 kilograms here. 90 kilograms here. So we're going to push on it with 50 newtons, nothing doing. 100 newtons, nothing doing. 150 newtons, nothing doing. Not moving. So since I added this 40 kilograms on top of the 40 kilograms, the 150 newtons, which would have been quite okay to start this thing moving. Watch. See that? It would have started moving it. But I don't have enough force to start it moving when this was originally there, right? 150 is not good enough to start it moving. What does that prove to us? Well, it proves that if I have more mass here, the surface has to have more normal force to keep it from falling through the ground here. And if there's more normal force, there's more contact between it, the surface, and the object. Ooh, that was weird. The surface and the object, and it'll require more force to keep it moving. Let me put this kid back on top. I've never seen that happen. That was weird. All right. So 150 newtons, not enough to get it moving. Finally, 200 newtons, not enough. There you have it. At 250 newtons, it started to move. Now, it probably would have started moving at a lower force. All right, and look, my applied force is larger than my frictional force. I have 81 newtons of net force. So it's accelerating. The speed is increasing. But if I push with less, so that my net force becomes 0, it's still moving forward, but look, it's not speeding up anymore. My F net is 0, my acceleration is 0, and it's moving forward. So what have we learned from this? We've learned that it's harder to start something moving than keep it moving. The force of static friction is usually larger than the force of kinetic friction because the coefficient is larger. We've learned that. We've also learned that the amount of contact between the surface and the object depends on the mass. The heavier it is, the more it pushes into the surface, the more the surface pushes back with the normal force, and there's more contact and there's more friction. Okay, so I know I've thrown a lot at you, and this is not the best situation to teach through a video, but we're going to try our best. Make sure you read the textbook. Make sure you watch the other videos I posted before you try some of the homework. So between this video, reading the textbook, watching the other videos, I'm hoping you'll get a pretty good understanding of this. We're going to do the best we can. So it's time to come up with equations that will help us calculate the amount of frictional forces we have when you have an object on a surface. So let's start with this one right here. Fs, the force of static friction. This occurs when the object is not moving, you're trying to start it moving. So imagine there's a book on a countertop and you're trying to push it. So there's the force push. There's the normal force right there, which is equal in magnitude but opposite in direction to the force of gravity. There's the force of gravity on the object, which is also known as weight, and we calculate that by knowing the mass of the object and multiplying it by the gravitational field strength. working against us, keeping it from moving, is the force of static friction, Fs. There it is. But how would you calculate the force of static friction? Well, there's an equation for it. The force of static friction with magnitude signs in it is equal to the coefficient of static friction. So that is where it depends on the two surfaces involved. And you would look up this number in a textbook like on page 101. And we multiply that coefficient of static friction by the normal force right there. But it's also within magnitude signs. It's also within magnitude signs. The reason we have to have magnitude signs is we could never write out this equation without the magnitude signs, because if we wrote it without the magnitude signs, we would be saying that the normal force and the force of static friction are not only equated through magnitude, but they're also equated through direction. That's not possible. The normal force and the force of static friction are perpendicular. We can never equate them here. It's not possible. The best we can do is only come up with a formula that allows us to calculate the magnitude. The magnitude is the best that we can do. Next, let's say now you've got the object moving. So the velocity is not zero. So the object is being pushed. So we now have the force of kinetic friction involved, Fk. So picture I'm pushing a textbook along a countertop there, and there's my force push. There's the normal force, which is equal in magnitude but opposite in direction to the force of gravity. There is the weight, or the force of gravity on the object, which is equal to the mass of the object times the gravitational field strength near the surface of the Earth, negative 9.8 newtons per kilogram. And now there's another frictional force working against my pushing. It's the force of kinetic friction, since the object is moving. How do we calculate it? Once again, we have to use magnitude signs, and we say the magnitude of the force of kinetic friction is equal to the coefficient of kinetic friction, mu case, a value you would look up, depends on the object and the surface involved. And for example, you'll find some on page 101 of your textbook. And then the magnitude of the normal force, which we know how to calculate. It's equal to the negative of the force of gravity. And we know how to calculate the force of gravity right there. So this allows us to calculate the magnitude of the force of gravity. It does not allow us to get the direction. Well, where are we going to find the direction from? Vectors have direction. How can I find direction? Well, you find direction from the free body diagram. And how do we get direction? Well, usually we assign the direction of force push to be positive, and therefore the direction of force of kinetic friction and the direction of force static friction is negative. Okay, well, why don't we do an example here, and it'll help us clarify things. At least I'm hoping, as we go through this distance learning. So let's say we have a 4,200 kilogram truck, and it skids, so the tires lock up and it's skidding. The tires are not rotating, and it skids to a stop. And let's say the truck tires are made of rubber and the road is dry asphalt. So on page 101 of our textbook, I would find that the coefficient of kinetic friction is 1.07. No unit. It's just a numeric way of describing that you have asphalt interacting with rubber. And what's the question here? Well, let's calculate the force of kinetic friction on the truck. That's the question. So the first thing that we would do is draw a free body diagram. So I'm going to draw the force of gravity on it, which is also known as weight. And as we remember, force of gravity is equal to the mass of the object times the gravitational field strength near the surface of the Earth, which is negative 9.8 newtons per kilogram. We're going to draw the normal force because the truck tires are on the asphalt, and the normal force, as always for us, is equal in magnitude but opposite in direction to the force of gravity. And then we're going to draw the force of kinetic friction, Fk. And we know that we have a way to calculate the force of kinetic friction, at least the magnitude of it. Magnitude signs are here. And it is equal to the coefficient of kinetic friction multiplied by the normal force. So basically this equation is telling you if you want to find out how much friction there is, you need to know the two surfaces involved because that's going to be a determining factor about how much friction you have. And you need to know the normal force because the amount of normal force there tells you how much contact is between the object and the surface upon which it sits. Alrighty, and that leads us to this equation right here. We're going to actually use that equation to find the magnitude of the force of kinetic friction. So we rewrite the equation, and then in the next line here, I replace normal force with negative force of gravity because I know that from the free body diagram. It's equal in magnitude, but opposite in direction. Next, I write, instead of force of gravity, I write mg, mass of the object times the gravitational field strength near the surface of the Earth. How do I know that? Well, that's the formula for the force of gravity on an object. That's the weight of the object. So I replace that. Now I've gotten to a place where I can start substituting because I know all of these values. So I put in the coefficient of kinetic friction, 1.07, no units. I put in the mass of the object in kilograms, and I put in the gravitational field strength near the surface of the Earth. Now, what's really important here is this is in magnitude signs. So really, whatever you get here is always going to give you a positive value, always, magnitude signs. We multiply it all together, and we get 4.4 times 10 to the 4 newtons. That's the magnitude of the force of kinetic friction on the truck. But I didn't ask you to calculate the magnitude of the force of kinetic friction. I asked you to calculate the force of kinetic friction. So I need a direction. How are we going to get that? Well, as I said in the previous part of this video, we get the direction from the free body diagram. Let's look at the free body diagram. We're going to assume that the truck was moving this way to the right as it was skidding to a stop. We're going to say, as always, that that's the positive direction. So by default, the other direction is negative. So that means I can put in a negative sign here and say that the force of kinetic friction is negative 4.4 times 10 to the 4 newtons. I got that from the free body diagram. Okay, so now listen, be patient with yourselves. Read the textbook. I hope you watched all this video. Watch the other videos I posted. Um, be patient. If you have a question, ask me. I'll help it. I'll help you out as best I can through the questions discussion thread, and we'll get through it. We'll get through it by being patient with each other. I'll see you soon. Bye.